So we saw some graph parameters like click, independent set. Let's see one more before I move on to the next set of topics. And this is a very important graph parameter again. It's called the vertex cover. So a set of, again, it's a subset of vertices that cover all edges. Okay. So S is the vertex cover if for every edge I or j is in S, or both. So I want to pick a subset of vertices such that for every edge, at least one endpoint is in this subset. Okay. So here is. Is this a vertex cover? Yes? No? Yes? For every edge, at least one of the endpoints must be circled. Then it's a vertex cover. Is it a vertex cover? Yeah. So 3, 4 is not. So let's say I circle this. So maybe I just go and fix it. 4 is not required. Okay, so says 4 is not required. Everybody agrees? He's not agreeing, but let's see if anybody disagrees. 4, 5 edge is not covered, right? So that is the vertex cover. So 1, 3, 6, 7, 4, 9 is a vertex cover. Okay. What is the natural question here? Should I ask for a maximum size vertex cover or minimum size? Why is max? If you take the entire vertex set, it covers every edge, right? So that's a maximum size. So the more natural question is minimum vertex cover. Okay. So this is again another important practical problem. So imagine this is a road network or something, and you want to, install fire stations at some of the nodes, so that at every street corner, at least in one of the endpoints, there is a fire station, or a fire station, ice cream shop, petrol bunk, whatever. So it's sort of like, you want to cover these edges, and you want to pick minimum number of vertices to cover all these edges. Okay. So what's the natural thing to do? If what would be a good algorithm? Some sort of a greedy algorithm. Maximum degree, right? Pick a vertex with maximum degree, because you want to cover edges. So pick a vertex which covers a lot of edges, include it into the solution, and then go and look at the remaining graph and say, okay, pick the next vertex which covers a lot of edges, include it into the solution. This is a fairly fast, you can implement it in n or n squared time, but it does not give you optimum. Okay. So exercise. So give an example where greedy does not produce an optimum. It's an important graph parameter. It comes up in many applications. If greedy works, then that would be a nice efficient polynomial time algorithm, but this is one of those NP-complete problems. Finding a minimum vertex cover, or in particular, is there a vertex cover of size k vertices, is an NP-complete problem. Let's see whether we can show it NP-complete. Right? We have this list of problems we know so far NP-complete. Does this look similar to any of this? clue. So suppose S is a vertex cover. What can you say about the remaining vertices? Let's say V minus S. Hmm? Hmm? Yep. So it is what? It's an independent set. V minus S is an independent set. You cannot have any edge. Why can't you have any edge across? Because then that means that edge is not covered by your S. Right? S is supposed to be a vertex cover. It covers all edges. If you delete S, what is left is an independent set. Okay? So now, problem is simple. You want to find a minimum vertex cover, find a maximum independent set. Right? So in other words, if you can solve minimum vertex cover problem in polynomial time, you can solve maximum independent set in polynomial time, because you get the minimum vertex cover, the remaining is the maximum independence. So if I want to ask the question, the decision version would be given G and K, does G have a vertex cover on K vertices? Yes, if and only if G has an independent set on n minus K vertices. Right? So then I can use the vertex cover subroutine to solve the independent set. Because if I want to know whether there is an independent set of size K, give me the vertex cover. Is there an independent vertex cover of size n minus K? And a solution to that will give you a solution. Okay. So these parameters are somehow nicely related, and so all of these are NP-complete. Okay. Now, as I said, there are literally thousands of problems, scheduling problems, various versions of tree, all kinds of things which are known to be NP-complete. The important problems which you need to solve, they are all NP-complete. Okay. So now, what do we do with NP-completeness? The problem doesn't go away. Now we have to look at other approaches. So what you stop worrying about, or what you stop trying to come up with, is a polynomial time algorithm for this problem. It's not hopeful. You're not going to get it. Okay? I mean, if you get it, you can get your $1 million prize and move on, right? Because you would have shown E is equal to NP, and that's one approach. You can still try. But the belief is that, NP-complete problems, you don't get polynomial time algorithm. So you move on and try something else. What are the something else you will do? And I'm actually teaching a course in IIT Jodhpur along with Manindra Agarwal. The title of the course is Beyond NP-Completeness. The whole course. This is an elective course for undergrads. Okay, so what do you do? There are various approaches people have done. Now, one thing which actually Manindra is doing, I'm not doing, I won't talk about it here, is that, we define this class as NP, P, NP-complete. What about other kind of classes of problems? And yes, there are literally tens of different classes of problems, because this whole thing is about what is the common characteristic about these problems, is what it's talking about. And people have looked at parallel complexity. These are called complexity classes, right? So parallel complexity classes. You look at space as one resource and measure and talk about complexity classes. So there are literally 10 or 20 or 50 different complexity classes. One, you can talk about relationship between these complexity classes, what are some interesting properties, and so on. So that is one nice theoretical approach to this complexity class. Okay. I won't talk much about it. But let's just come back to what does it mean by a problem is NP-complete, that you don't expect a polynomial time algorithm. You don't expect a polynomial time algorithm for the general instance of the problem. But if you know something special about the problem, maybe you can do better, right? For example, this SAT problem. So let me write down what is this direction special instance. this SAT instance, suppose somebody tells you that every clause has only 2 variables, then you can solve it in polynomial. There is a nice graph version of it. You can translate it into some reachability problem, can you reach x and x bar and things like that. You can model it as a graph problem and you can solve it in polynomial. So for example, these are, the NP-Completeness tells you that the most general instance of the problem, you don't expect a general purpose polynomial time algorithm to solve it exactly. But if you know something about the problem, maybe you can. So for example, SAT. Or let's talk about the click problem, right? You know what a bipartite graph is? Okay, but not many. That's why I asked whether they've done a graph course. They have. Okay. So you done. Okay, you know what a tree is, right? You know what a tree? What is a tree? It's a connected graph with no cycle. I want to solve the click problem, but I am told that the graph is not a general graph, but it's actually a tree. I want to find the maximum click in a tree. How much can it be? Remember what is a click? It's a subset of vertices where every pair is mutually adjacent. So, how big a click can you find in a tree? 2, right? You cannot even have a 3 click, because 3 click means it's a triangle. But the tree does not even have a cycle, right? So if I tell you it's tree, then all you have to do is to look at and see if there is an edge. Yeah, there is an edge. That's the maximum click you can get, 2 vertices, linear time, right? Very fast. So, click in a tree. Okay, this is actually a trivial example, but let me write it this way. For example, a bipartite graph, right? What is a bipartite graph? That you can partition the vertex set into 2 such that edges are only going across, right? What kind of a click can you get in a bipartite graph? In what context did you learn bipartite graph? Matching. Matching, right? So, an important property of bipartite graph is that you cannot have odd cycles. Tree cannot have any cycle at all. In a bipartite graph, you can have cycles, but every cycle is of even length. If at all there is a cycle, it's an even length cycle. So a bipartite graph cannot have an odd cycle. So how big a click can you get in a bipartite graph? Can you get a click of size 3? No, that's an odd cycle. You won't get. Can you get a click of size 4? Why not? Because there will be an odd triangle sitting inside, right? A click of size 4 means every pair of them is adjacent. So in particular, 3 of them is adjacent as a triangle. So you cannot even get a click of size 3 or 4 or 5. Maximum size click you can get is 2. Again, it's a problem is very trivial there in a bipartite graph, right? There is something called planar graph. Right? This is have you seen a planar graph? So a graph is planar if you can actually draw it in a plane without any crossing. Okay. So is this planar? Well, this is not a planar drawing, but this graph is actually planar because I can draw it like this. So this is a planar graph. It means I am drawing this graph in the plane with no 2 edges crossing each other except at a vertex point. Okay. But if I have one more vertex, a click on 5 vertices, try and draw it in the plane. I can be adjacent to this. But if I want to make it adjacent to this, I have to cross some edge. Okay, so This is a complete graph on 4 vertices, but if I want to get a complete graph on 5 vertices, the graph is no longer a planar, and there is a nice characterization which says that you cannot have K5 complete graph on 5 vertices sitting inside a planar graph. So the maximum click in a planar graph can be at most of size 4. So can you find the max click in planar graph in polynomial time? How will you do? Try all subsets of size up to 4. What is the maximum possible? That's like an n power 4. Right? It's n power a constant, so it's a polynomial time. Right? So what's the moral of the story? The point is that the problem is NP-complete in general graphs or general instances, but if you know something about the input, then a lot of these problems click in bipartite graphs, planar graphs. For example, vertex cover. This is hard in bipartite graphs. There is a nice theorem which says that you can use matching to solve, find the maximum matching in bipartite graph. From there, you can actually get a minimum vertex cover in a bipartite. So, if you know something about the input, maybe you can solve the problem in polynomial time. So there is a whole class of graphs actually called perfect graphs. There is a whole book on perfect graphs, okay? Caudal graphs, interval graphs, permutation graphs. These are all, you can define some interesting structure about the graph that defines your class of graphs. In that class of graphs, you look at these hard problems and see whether they are solvable in polynomial time, and they can. And in fact, in the real world, your graphs are probably not very general enough that you can exploit some input properties and then design polynomial time algorithms, even though the problem may be NP-complete in the general graph. Okay, so this is one direction to deal with NP-completeness, to look at, so people, there is I told you there is a whole book on perfect graphs, so you can see papers talking about polynomial time algorithm for this problem in this kind of graph. So this is one approach to deal with NP-completeness. The other big industry is approximation of. Okay, and you have some lecture on this today, right? Tomorrow, Saurav is going to talk about, right? So you will see more about it. So what is the idea here? Well, so we said the decision problem. The NP-completeness theory is all about decision problems. These decision problems of click or independent set or vertex cover, TSP, these are all NP-complete. Which also means the optimization problem is even harder. You don't expect a polynomial time algorithm. If I want a minimum vertex cover or max click, because if you solve that in polynomial time, you can solve the decision version easily anyway. So all of these optimization problems are NP-complete. You don't expect a polynomial time algorithm. So what do? We relax. Okay, I don't want minimum vertex cover. Give me something close to the minimum. I don't want the shortest traveling salesperson tour, but something close to the optimum, right? Now, problem is, how do I know this solution is close to optimum when I can't even compute optimum, right? So, this is something, for example, in engineering, electrical engineering, people routinely try because they have this complex problem in VLSI layout, which which is an NP-complete problem. So what do? You come up with some heuristic. Like, for example, for vertex cover, you all said, oh, pick the vertex with maximum degree included in the solution. Sounds like a good idea. For TSP, I am here, I'll go to my closest city and then visit and then closest. So you can come up with these kind of greedy heuristics. And typically in engineering, what they do, if they have a real world problem to solve, they apply this heuristic, get the solution and say, okay, here it is. I have some solution. I don't know whether it's optimum or not, but I got some solution. I need to solve it and move on, right? Now, but in theory, we are not happy with that. We want to do a little more analysis about the solution you come up with, how close to the optimum it is. So we want to compare it. So there is this notion of approximation ratio. That if the opt value is something like 100, and I'm talking about a minimization problem, and my solution is never more than 200, so I am at most 2 times optimum. So minimization problems, I'll produce something larger, but my solution, suppose I am able to show that, in particular, I want to show it's at most 2 times opt, then I care about this approximation ratio. How close to the optimum do I get in polynomial time? So you'll see more examples in tomorrow's lecture, but the real challenge here is, how do I even know this without even knowing what the optimum is, right? Well, actually, I'll do an example today, which you might also see tomorrow. And okay, let's come back to this vertex cover problem. Okay, let's do vertex cover. There are lots of interesting machineries get thrown out here. Have you done a course on linear programming? Not even optimization, simplex. Oh, simplex. You saw it, right? You saw about linear programming. Let's look at linear programming formulation of vertex cover. Okay. So let's look at vertex cover problem. You are given a graph C, and vertex cover is a subset such that for every edge, I or j is in it. And you want to find a minimum size subset. Let me phrase it as a linear program problem. Okay, it's in very interesting, it's very simple. So you are given a graph, so that means there are vertices, there are edges. Now I want to pick a subset of vertices such that every edge has one endpoint here. Okay, so let's formulate it as a linear program and see how it will do. So what do you want to do? Minimize or maximize? Linear programming is all about, minimize or maximize subject to some linear constraint. So this is a minimization problem. So I want to minimize. What is it I want to minimize? Well, I have to think of what are the variables here. Let's create a variable for every vertex. Okay. The semantics is the 1 means that that vertex is into the solution, and 0 means that it is not in the solution. Okay. So my graph has n vertices. So V1, V2, up to Vn. I decide to pick some of these vertices. So if I pick a 1, if I pick a Vi, and Vi is set to 1, means that that is included in the solution, and 0 means it's not included in the solution. So what is it I want to minimize then? Yeah, number. Can you say it in terms of, so let's call these variables x1 to xn. These are my linear programming variables, where I set a variable to 1. So the linear program will solve. If it gives me 1 means that I'm going to include it in the solution. If it gives me 0, I'm not going to include it in the solution. So what do I want to minimize? Summation xi. I want to minimize the total variable. Each variable is going to get 0 or 1, so I want to minimize, because this summation xi is precisely the size of the set in the solution. What are the constraints? Right? This is all I want to do. I'll pick every xi is 0, minimize it. But what are the constraints? I want to satisfy the constraint. This is the constraint. Right? For every ij in the edge set, xi plus xj better be at least 1. Right? This means that at at least one of this is into the solution. And let's say every variable gets a value 0 or 1. This is it. This is a very nice linear programming formulation. This exactly models vertex cover. I want to minimize summation xi such that for every edge in the graph, this is the input. The constraint is that xi plus xj is greater than or equal to 1 and xi is in 0 or 1. So you saw simplex for linear programming. That is really not a polynomial time algorithm, but there are, in fact, linear programming coming up with polynomial time algorithms is one of those important open problems in the 80s which was solved. There is nice polynomial time algorithms to solve linear programming. But this is not a linear program. Why is it not a linear program? You can't get this, you can't put this constraint in a linear program. Linear program, you can say xi is greater than or equal to 0 or less than or equal to 1. But once you say 0, 1, this is actually a 0, 1 integer program, integer linear program. Okay? Can I solve this in polynomial time? Linear program can be solved in polynomial time, but integer program turns out to be NP-complete. Lo and behold, we just proved it NP-complete. Look at it. What did we do? We reduced vertex cover to integer program. We know vertex cover is NP-complete. So we have just proved that vertex cover, integer linear program is NP-complete. Right? Because we took the vertex cover problem, general graph, and you want to know whether there is a k-sized vertex cover. We just said, we formulated an integer. So this is NP-complete. Okay? So there is no hope of polynomial time algorithm. So why did I formulate it? Well, it's an interesting NP-complete deduction. But okay, so now I'm going to use this to somehow get an approximation algorithm. Okay, so this is the nice exercise. That's why I did this. So what do we do? So let me relax this condition and say xi is greater than or equal to 0. Okay. And now this is a linear program which can be solved in polynomial time. So solve the linear program. But unfortunately, now this does not exactly model vertex cover, because if I want to model vertex cover, I have to put this constraint. Once I relax it like this, it's no longer a modeling vertex cover, but it is modeling something related to vertex cover. We'll figure out what it is, but at least something I can solve it. Now I can solve this LP in polynomial time, right? I solve the LP in polynomial time, and whatever LP puts 1, I include it in the solution, 0, I exclude it in the solution, and would that be a vertex cover? Because I know I put this necessary constraint for vertex cover. So I solve this LP, and whatever LP puts 1, I include it in my solution. Whatever LP puts 0, I exclude it in the solution. Is that fine? Yeah, that's actually fine, but LP does more. It may not just put 0 or 1, because you just said this. LP may put some variable 1 by 8, 1 by 23, half, because LP is going to put fractions. I don't know how to interpret it, right? Because this is not an exact modeling of vertex cover if I remove this constraint. But reason I removed its constraint is because we can solve it in polynomial time. This linear program is solvable in polynomial time. Suppose I solve it. Now, here is my, I'll get a solution for vertex cover in the following way. Pick Vi in S. Can you see this? Visible? If xi is greater than or equal to. I'm going to do a rounding. So I solve the LP. LP gives you some fractional values. LP, the reason I do LP is because that's what I can solve in polynomial time. Integer programming I cannot. So I solve the LP. In polynomial time I solve the LP, but it throws me a lot of fraction values. So now what I'll do, I'll round up. Whenever a variable gets greater than or equal to half, I promote it to 1, and otherwise I throw it out. Now I claim 2 claims. S is the vertex cover. The second claim is the number of vertices I have picked is at most 2 times the optimum. It may not be optimum vertex cover, but it's never more than 2 times the optimum. Why is S the vertex cover? Well, every edge must be covered. Is it covered? Why is it covered? Because if you pick any edge, this constraint must be satisfied because I solved the LP. So one of these variables must be greater than or equal to half. It's not possible that both are less than half, then I can't satisfy the constraint. So one of this LP actually made it greater than or equal to half, and I promoted it to include it in my vertex cover, so it is a vertex cover. So what I produced is the correct solution, and this is the interesting important claim that it is never more than 2 times optimum. Why? Because, okay, what can you say about optimum value of LP and optimum value of integer linear program? Which is smaller? Something with this constraint or without this constraint? And solve this LP, which value would be smaller? It's a minimization problem. If I remove this constraint, I should be able to go even smaller, no? It's a minimization problem. I say, okay, you want to minimize this subject to these constraints, and it gives me a solution. Now I remove a constraint and say, okay, you don't have to satisfy this. I'll actually even go down, right? Because any solution for this is also a solution for this. But I might go even smaller. Okay, so I would say this is less than or equal to opt IL. Okay, so this is an important observation because I take this LP without the constraint, and with the constraint, which value would be small? It's a minimization problem. If it's a maximization problem, you will argue the other way. So optimum value of LP is less than or equal to optimum. Okay, so now let's just come back, prove. So this proof is easy. The second proof, how many vertices I have picked? Well, cardinality of S is, I want to say that at most 2 times summation xi 1 to I equal to 1. Suppose xi star is optimum of LP, and I pick into the set if xi star is greater than or equal to half, then whatever I have picked is at most 2 times, because what did I do? If it's greater than or equal to half, I pulled it to 1, otherwise I brought it down to 0. So I might have at most doubled this solution, whatever this solution was. But this solution is exactly the 2 times LP opt, and we just saw that LP opt is less than or equal to 2 times ILP opt, and ILP opt is exactly size of the opt vertex. Okay, so there are lots of, let me summarize what we did. We modeled the vertex cover problem as a linear program, solved the linear program because that's solvable in polynomial time. Because I want to use something polynomial time, solved it. It gave me some fractional values, and I rounded the values up to get a vertex cover whose value is at most 2 times the optimum vertex cover. I don't know, this is what I told you, I don't know what is the optimum vertex cover, but I know a bound. So I can use that bound to sort of relate my solution with the optimum. Okay, so to summarize, first of all, there are lots of machineries you can use. I can, it's again to show you this connection that I'm looking at a graph problem. I can just go to linear program, which is very well studied, completely new domain, use some theorems and algorithms from there, do some rounding is one moral of the story. The other thing is that you may not know the exact optimum value to compare your solution, but you can get some polynomially computable bound. Compare it with that. So you're going to see this kind of a theme tomorrow in approximation algorithms. You will see a lot of it. Interestingly, this high degree vertex rule you said, right? So I picked the highest degree vertex included. That is not a very good approximation. You can't, for example, show this ratio 2 with that. It can produce a solution which is far away from the optimum. Far away in the sense that it can be as bad as like log n times the optimum. Okay. So these are all the kind of interesting structural theorems you will see in approximation. So as an area, there is again several books on approximation algorithms. The idea is that many problems you want to solve in practice are NP-complete. So you want to relax that I want optimum, I am willing to go close to optimum, but what is close is very hard. So this ratio is the key thing one optimizes here. Not so much the running time. Yes, we want polynomial time, but how close to the optimum would I get? And we want a qualitative measure of it. 2 times, 3 times, 1.5 times, there are algorithms which can get 1 plus epsilon close to the optimum. Okay? And there is a trade-off with respect to the running time. And there is a notion of hardness also here. That people show that, oh, this problem not only is NP-complete, it cannot even be approximated well unless something happens. There is this complexity classes related to approximation, it opens up all kinds of. Okay, so that is this other direction of dealing with NP-completeness. One can do is that exact exponential algorithm. So you live with the fact that if I really want exact algorithm, you have to settle for exponential algorithm. But okay, so n has to be in the exponent, but I want to improve the base of the exponent. Improve from 2 power n to 1.5 power n to 1.2 power n. How low can you get on the base? So that's the approach here. So I'll give an example too. So we already saw in the context of traveling salesman problem that it's a hard problem. Brute force algorithm takes n factorial. Now using dynamic programming, we can improve it to 2 power n times n square. We are still sitting in the exponential world, but within the exponential world, we are moving to lower exponential functions. Okay, so that's we did it in TSP. Let me just show it an example in for 3 sat. Okay, so let's do. Let's look at 3 sat is a special version of sat where every clause has exactly 3 variables. And some clauses like this, there are n variables. Now, I want to know whether this formula is satisfiable. One brute force algorithm I know is 2 power n, right? 2 power n times some small running. So try every 0-1 assignment to all these n variables. Once you set an assignment, go to the formula and check whether it is satisfied. If not, try a next assignment and then you go on like this. You want to improve this too. Right? So here the idea is not, okay, it's a NP-complete problem, so we have to settle for exponential algorithm. and I don't know what is an approximation here. So I would just go and say, try and see if you can improve the base of it. Can I avoid running through all 2 power n assignments? Okay. Clearly, there is some assignment which we should not even try, right? For example, any assignment that sets x1 to 0, x5 to 0, and x7 to 1, don't even bother exploring, right? Because that's falsifying this clause. So how many assignments would you save in that process? No. No. Wait. So what is my question? How many assignments for all the variables with x1 equal to 0, x5 equal to 0, and x7 equal to 0. There are n variables. You are looking at assignments on the n variables, 2 power n of them, out of which I am just saying avoid these assignments. So, how many assignments do you end up avoiding? How many of the 2 power n assignments for the n variables set this? Okay, let me ask a simpler question. How many of the 2 power n assignments set x1 equal to 0? Two power n minus 1, 2 power n by 2, right? Because half of them will set x1 to 0, the other half will set x1 to 1. So, how many of these assignments will set this? 2 power n minus 3, because all I am saying is I am fixing an assignment for these 3 variables. For the other variables, you have all the choices. That's 2 power n minus 3, and that's what you save, right? Just by looking at one class, I learned some heuristic and I say, okay, don't do this. That means out of the 2 power n, I'm going to do 2 power n minus 3 is what you said, so that's 8. So that's like 7 into 2 power n by 8. That's the number of assignments you have to take, just by looking at one class. If you look at another class, you may save some more. Okay? But that is still not improving the base of the exponent, but that is just saving a fraction of the assignment. I'll use the same trick and I'll tell you a way to improve the base of the exponent. Let's do it the following. I'll write a recursive algorithm. So what we'll do is the following. So think of it as a branching algorithm. I start with the root. I set x1 equal to 1. You know that to satisfy this clause, I just looked at the first clause. To satisfy that clause, x1 has to be 1, or x5 has to be 1, or x7 has to be 0. Okay. In each of the branch, what do? I set x1 equal to 1. It cleans up a lot of other classes. Wherever there may be another x1, those clauses are removed. Maybe wherever there is an x1 bar, you have to delete that variable. You do all that simplification, and then recursively check on the remaining formula whether it is satisfied. So recurs here, and recurs on the remaining formula. So one variable is eliminated. I know that any satisfying assignment should try this or this or this. Okay, no, this is not a great algorithm. So, no, I'll do a little bit more. I'll do a 7-way branch. Okay, so let's look at x1, x5, and x7. These are the 3 variables that appear in the first clause, and there are totally 8 possible assignments for these 3 variables, out of which 1 is not allowed. Correct? Which is not allowed? This, whatever I wrote down, x1 0, x5 0, x7 1 is not an assignment I want to explore because that will not satisfy the formula. I can as well decide and abandon that branch. So I do a 7-way branch. So here I would say x1 equal to 1, x5 equal to 1, x7 equal to 1. And then something else here, something else here, something else here, and do my simplification on these 3 variables. Not just on this class, I go run over, and once I set an assignment, see the 2 power n is all trying all possible assignments, so something similar, but only focusing on these 3 variables. Instead of trying all the 8 assignments, I'm going to do 7 assignments. And then I simplify the formula, and then I ask in the remaining formula, is it satisfiable? If I set this and if the remaining is satisfiable, good, I'm done. If not, I try this. If the remaining is satisfiable, I'm done. Otherwise, in any of the 7 branches, I get no, 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 no. I know that it is not satisfiable. Right? Now let's write down a recurrence relation for it, solve it, and see what we get. Is the algorithm clear? I mean, recurs on the remaining variable. So if I write C of n is the number of steps or number of assignments explored in this algorithm, can you give me a recurrence relation? Because it's sort of a 7-step algorithm. Right? Try this assignment and recurs. And if you are happy, stop. If not, try this next assignment, recurs. Now, how many variables on which you are recursing here? N minus 3, exactly, because you have set these 3 variables. So T of n is what? T n minus 3 plus T n minus 3 plus T n minus 3, 7 times T of n minus. There is one variable, you just set it to assign that and stop. That's sort of the base case. So what is the solution to this? You can keep expanding it and figure it out. It will be like 7 square into T of n minus 6. 7 cubed into T of n minus 27. So 7 power what? How many times you have to expand it so that it becomes like 1? No. N minus 3. Yes, it's 7 power n by 3, which is 7 power 1 by 3 whole power n. Right? Is this smaller than 2? Why? This 8 power 1 by 3 is 2. So this is smaller than. So now you actually have improved the base of the exponent from 2 to something smaller. So the initial trick said, oh, avoid exploring all these assignments. Actually, you improved it from 2 power n to 7 by 8 2 power n. That was only a fraction of 2 power n. You did not improve the base of the exponent. Whereas here, you can actually improve the base of the exponent. And so this is actually some 1 point something something. Okay. This is again another industry. It opens up a whole direction. You can say, oh, okay, why do I look at only this class? I look at this class and that class and do some clever heuristics, branching, keep doing it. And currently, for example, for 3SAT, the current best stands for something like 1.5 power n. Okay, so this is one big direction to deal with NP-Completeness, where you say, okay, I mean, again, there is a recent book on, exact exponential algorithm. Lots of different techniques, branching, divide and conquer, dynamic programming, all of this is used. And we can talk about exact exponential algorithms is one big area. So I'm going to add to this list. So here, so in In each one of them, you want to exploit special instances, you want to exploit some properties of the input. In approximation algorithms, the challenge is to measure how close your solution is to the optimum. And here you want to improve the base of the experiment. Okay, the final direction, there is nothing final about anything, but since we are close to the time, I will just give you one last. This is again a more recent direction in the last 20-25 years. Is this notion of parameterized. So what you do is you look at the, so now we are not necessarily looking at the optimization question, but okay, let's get to the vertex cover problem. You're given G and K. So the question we are interested in is, are there K vertices that cover all edges? Okay. So the decision version is NP-complete. For the minimum vertex cover, we saw a 2 approximation algorithm. You model it as an LP, solve it, do a rounding, gave an approximation algorithm. Okay. But suppose I am interested in, I am not interested in minimum vertex cover. Somebody told me that this graph actually has a vertex cover of size 25. So I want to find it. In particular, I want to know, I just want to know if there is a vertex cover of size 20. Okay, let's say K is small. Is there a vertex cover on 20? So 20 is some parameters. This is all about, look at some parameters on the input. So if this is the question I want to ask, how much time do you need? How will you solve it? Is there a vertex cover on 20 vertices? Can you give me a brute force algorithm for it? Not minimum vertex cover. I mean, minimum would be nice if it is less than or equal to 20, but that's too much. But it need not be the smallest. Smallest may be 5. But give me a vertex cover of size 20. What would be a brute force algorithm? Exactly. Try every subset of 20 vertices. Check whether they cover all the edges. How much time does that take? Yeah, what is the term? N to, well, 2 power n, no. If I really only care about 20, n may be very large. But if it's only 20, it's NC20, right? It's n choose 20, which is roughly n power 20. Clearly upper bounded by 20 because it's n into n minus 1 into n minus 2, some 20 terms. So it's n power 20. Is actually a polynomial time algorithm in my definition, even though I said 20 is still a large number. Now you can't really avoid it because it's an NP-complete problem. So something has to be sitting on the exponent. K is sitting on the exponent. So what? So it's fine. So you should be happy about it already. No. So in general, if I have a K, then I have an n power K algorithm. K has to be in the exponent. How about 2 power k n square kind of an algorithm? Don't make k sit on top of n, but maybe sitting on top of some small constant. And NP-completeness does not rule out anything of that, of this type. If k is large, it's still an exponential algorithm. But at least for small k, this is a much better, more feasible algorithm than this. So parameterized complexity addresses this question. There is an input. There is also a parameter, which could be, in this case, I chose it to be the solution size, which is likely to be small, but it could be anything. So in your input, you can think of it as a multi-dimensional analysis of our problem. In your input, there are, if you have a VLSI problem, there is a graph, there is something about how many crossings are there, there's something about the degree of the graph. There are various different parameters are there available. Now, simply classical complexity just talks about what kind of a running time can you get as a function of the input size alone. But this now you say, okay, there is this input, there is this parameters which are likely to be small. I'm okay to be exponential on the parameter because which is expected to be small, but on the rest of the thing. So ideally, for example, something like this would be even better. That I'm exponential on the small parameters, but the rest of the thing is polynomial. What sort of problems have this kind of a behavior? Now this is a lot more general because what is the parameter is something your choice. There is this graph, there is input, but maybe how close to bipartite graph the graph is, maybe the parameter. Right? Something which I can solve in bipartite graph in polynomial time. Okay, but this is a little more than bipartite. You have to properly define what you mean by little more than. But if it is not very far from bipartite graph, I allow that exponential in that distance, but the rest of it is polynomial time. What kind of problems have such an algorithm is the theme of parameterization. So for the vertex cover problem, for example, there is such an algorithm. I'll tell you that algorithm, it's not very hard. So it's again like the branching algorithm we saw for satisfiability, but we're going to do slightly different branching. So now, is there a vertex cover of size 0? When does a graph have a 0-sized vertex cover? Remember, what is a vertex cover? It's a set of vertices that cover all edges. There are no edges in the graph. Right? There are no edges in the graph. There may be a lot of vertices. There are no edges in the graph. Yeah, I don't need any vertex coverage. So the only graph, so this is easy. Right? I just have to check the graph to see whether there is an edge at all. Okay, so this is like a base case for us. So this is easy. So now I'm going to get to this base case. So I pick an edge. Suppose ij is an edge. Any vertex cover should contain I or j for sure. Right? So I will branch. Like the way in the SAT, we said any satisfying assignment should give one of these 7 possible assignments to the first 3 variables. Right? Similarly, any vertex cover should pick I or j for sure. So let me try both. So in one branch, set, put I in S and recursive. So I already have picked one vertex and I'm looking for a vertex cover of size k. So recurse check vertex cover on k minus 1 vertices in G minus I. And here, so I'll try this, and if I succeed, then good. I pick that k minus 1 vertex plus I, that will cover all the edges, and I know I got a vertex cover of size k. In the other direction, I try with j. If both of them say no, then I know there is no vertex cover because I tried with I, tried with j, and neither of these works, and I should say no. The k drops at every step because I am looking at k minus 1. What do I do? In the next step, I pick some other edge in the graph G minus I, try one with this vertex, try another, and so it's like a 2A branch at every step. And when does it stop? What is the base case of this recurrence? This recursion? When k becomes 0, I'm checking. I'm checking is there a vertex cover of size k? The next step k minus 1, k minus 2, and eventually k becomes 0. And in that I have a graph. Is there a vertex cover of size 0? Well, I know I can do that in polynomial. Answer is yes if there is no edges, and answer is no otherwise. Okay. So the k gets dropped at every step. So the height of this branching tree would be like k, and each step I am doing a 2a branch. So the overall thing would be like a 2 power k steps, and each step I am doing some polynomial time to remove a vertex, delete some edges, and so overall this algorithm running time, you do a careful analysis, it will be like 2 power k times n. Okay. This is a much better algorithm than trying all possible subsets of size k, which is like an n power k. And simply because here we have this extra structure of the problem which tells you that, I can't omit both I and j, one of them must be there in this. And here again there is this game, okay, can you improve the base of this 2? And answer is yes. There has been a lot of work over a series of papers. Currently we know it's like 1.3 power k plus n. There is a, similar to NP-Completeness theory, there is a notion of hardness here, where you know that, even on this parameterized setting, there are problems where you cannot get an algorithm of this type. K has to be on the exponent. And so this is about 25 years old. 91 are the first papers that started. So that is another direction to deal with NP-Completeness. So that concludes what I want to say, hopefully. So you got an idea of what NP-Completeness is, the famous conjecture about NP-Completeness, and this is a very hard to research direction in algorithms. I would say something like approximation, parameterized complexity, exact exponential algorithms, special classes of input. Okay. I think I will stop. Any questions, comments, anything? So I don't know whether Ramanujam mentioned about our institute and what programs we offer or something like that. So maybe I have a minute, so I will use it to mention about. So how many people have heard of the Institute of Mathematical Sciences? Now you know, because several of us are from there. So it is, even for teachers it's useful, because if you have students. So it's a institute funded by Department of Atomic Energy, central government. We have only PhD program. That's why you don't hear about it as much as you know about IITs, because we don't have an undergraduate program. We only have a PhD program. And 4 disciplines: mathematics, physics, computational biology, and theoretical computer science are the subjects where we are pursuing research. Admission to our PhD program is through an entrance test called JEST, Joint Entrance Screening Test. So this year's exam, I think, is in next couple of weeks. And the advertisement comes sometime in October, November. The exam is in February. There will be an interview followed by this in April, May, and then our semester starts sometime in August. So important, couple of important information. Every PhD student gets a stipend. Currently, I think it is about 25,000 rupees plus book grant and conference grant and various other things, hostel accommodation. There is another important information you may not know. You don't need a master's qualification. You can finish your undergrad and apply for JEST and directly join for PhD. It's called an integrated PhD. Along the way, you pick up a master's degree by writing a thesis. I would like to encourage good students. We do only theoretical computer science, and there are a lot of prospects. Country always needs serious researchers, and it's a very nice profession. Your teachers can tell you about it. So I encourage students to apply for this PhD. If you have any questions about NP-Completeness or about JEST or about PhD programs, feel free. All right. So we also have summer internship program where typically over 1 month, 1 to 1.5 months, we will have some modular lectures. This is the plan we have been following the last few years. There will be some advanced courses, something like this, over a month. And you get to also work with some faculty member and get a taste of research, read some papers, or read some advanced books, material over the period of a month and a half or something. In addition, actually, a lot of engineering students also do a 6 months or 4 months internship. Some programs actually require a whole semester of internship, and people actually come and work with us on. It's just basically you get a taste of research through this. Many of this can be informally arranged by talking to people. You met various people who have come here. You send an email to them and say, okay, I want to do an internship. Can I? Especially people in Chennai, it's no problem because it's a question of your time versus my time. Okay, so we fix the time, and you are welcome to come and discuss about anything. So people outstation, there is this accommodation. Our guest houses are limited, so it's a little more difficult. And we are a small group. We are 9 people in computer science, and everybody is busy. So you are not going to get an overwhelming response when you send an email. Okay? But you should persist. You should, especially because everybody gets hundreds of internship mails from various people. So you have to somehow distinguish yourself. You send an email, remind us that you attended this program. So somehow it just sort of clicks in our mind. Otherwise, you get hundreds of them. And but independent of the internship, especially people in Chennai, I think you should just we have a very good library. Take advantage of it. Just drop by. Library is open for everybody. But you want to meet us, send an email, come drop by, talk about something. Okay. So, thank you very much. Yeah.
On behalf of the participants, I would like to express my thanks to Dr. Venkatesh Raman. He has spent 2.5 days with us. That's remarkable. Having taken time to be with us to encourage faculty members from other colleges and the students especially. Thank you very much, sir.